Yeah, go ahead.
I had actually sent an email, but when I calculated the initial temperatures at time equals 0 for the rod, I found that the first or for the boundary condition when U is 0, um, it was 70 degrees Celsius. But then at the last boundary condition, you had told us that the boundary condition was it was 30 degrees Celsius.
Mhm.
But then when I calculated using that equation that you gave us, the 70 plus 2 or 70 plus I think it was,
Yeah.
yeah, that equation that you gave us, it also ended up becoming 70. So does that mean do you want us to like negate that and just make that 30?
No, there are two ways to address that. So one is that consider that the initial conditions are before the time has started. So it is at the time t is equals to 0 minus seconds. So it is just before the boundary conditions are applied. Those are the initial conditions. So basically for the very first time step at time t is equals to 0 minus, basically you can consider that as the initial condition, and immediately after 0 plus seconds you actually got at as 30 degrees centigrade. So that is one way of considering. Another way I was basically thinking, so you can basically change the boundary condition. Just let me actually share the document camera. So the initial conditions for the homework problem is given as u at time t is equals to 0 for all the grid points, can also be denoted by this, is equals to 70 plus sine 2 pi xj, right? That was the given basically.
Yeah.
Yeah. So one way that you can basically make that inconsistency go away is just by considering this additional term. So when xj is 0, you have 70, and when xj is L, you have actually it should be minus 40. Does it make sense? Does it now satisfy all the boundary conditions at the start and the bottom? Basically, when xj is 0, you have uj 0 is equals to 70. This also matches with your boundary conditions. When xj is equals to L, then u0 and ul0 would be 70 minus 40, which will be 30. Will that be okay?
Um, yeah, that makes sense.
Yeah.
So okay.
So basically what I am asking you guys, I mean, if you have already done that problem without considering this extra term, that's fine. I do not need to consider it. But in case you are seeing this inconsistency, you can add this to the initial condition. So I will just post an update on the beach board as well. So in case you have already solved it, it's okay. But if you have not, you can basically add this extra term in the initial condition. That will basically drive away all the inconsistency you're observing in the boundary conditions. Okay.
Okay. So that means it'll actually change all the values then, like before I had certain number of values, but now it'll change. I think that'll make sense now. Yeah.
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 I mean, it is just one extra term to be added in your code, so should not be like too much of work, I believe. But in case you have already solved it, it's okay. I mean, you don't have to change it. You can basically you can stay with that. That's okay. So what I was basically mentioning is that time t is equals to 0 minus seconds, where it is just starting. These are the initial conditions. And boundary conditions are applied at time t is equals to 0 plus second. That's what I was basically mean when I was discussing the first first method or first route to address this inconsistency. Okay, does it make sense?
Yeah, this makes sense now.
Okay, great. Any other questions, guys, regarding the homework number 2?
Yes. I email you asking about the MATLAB code, how to store the loop,
Okay.
and then we after running ax equal b, and it return only one value. So I want to store it in the vector value. So
Okay.
can you help me?
So how about okay, let's deal with that. So can you share your code? Share your screen. I can look at your code and I can basically see what is the problem. Can you share your code? I'm stopping my share. It's fee, right? Uh, sorry, I'm not getting you any response or feedback. Are you
Oh
there?
yes, yes. I haven't get MATLAB running, so
Okay,
sorry.
then, okay, let's do what? Let's go through the lecture, and at the
Yeah, sure,
we
sure.
will go
Thank you,
through your code and I will basically try to address that,
thank you.
whatever issue you have. Okay, there are maybe other emails I'm getting as well. So I have not been getting the time to respond, but let's say I will stop a bit early today so that we can address your individual queries regarding your homework problem. And if you have any difficulty in implementing any specific snippet or specific code, please let me know, and I will try to address that. That should be okay. So having said that, let's actually come back to the lecture part. So today we will continue our discussion on eigenvalue problem, eigenvalues. And we actually saw that eigenvalues basically are for any square matrix A, we saw that there are certain number of n scalars such that they satisfy this equation where each scalar has got an eigenvector associated with it. So if I have lambda 1, so I should have a corresponding eigenvector associated with it, which is, let's say, vi lambda I v. So vi is basically an eigenvector corresponding to lambda I. So basically eigenvalues are just the scalars quantities which actually satisfies this equation or this characteristic equation, which is that so each eigenvalue has got an eigenvector associated with it, and the eigenvector has a property that when it's multiplied with the matrix A, it does not change its direction. The direction remains same, but it only scales up or down depending on the scalar quantity. And to solve for the eigenvalues, here we actually solve this equation. We solve the determinant of A minus lambda I equals 0. That will give us a polynomial equation in nth degree. This will result in nth degree polynomial. And the roots of which are the eigenvalues. And the roots can be real number or can be complex number. Can be real as well as complex. Okay. So I hope everybody is with me so far on this. Yeah.
Yeah.
Any questions, guys, so far on this? There are no more questions. Then let's see what else we can or we need to do with or we can do with the eigenvalues. Eigenvalues basically, as we saw that we took a very specific example in the last class. Let me actually see my notes. Okay, So we took just one example 9.1, which is 2 by 2 matrix, and we got the eigenvalues and we also got the eigenvector. So today what we are going to see that we're going to take another example from the textbook. Just give me a second. Yeah, so if you have your textbook in front of you, you can basically note down example number 9.5. That's what we are basically right now taking to see what we can learn from that. So example 9.5 says the matrix A has got the 3 by 3 matrix is 6, 1, -2, -2, 6, 2, 0, -1, 8. Okay. So is everybody following what we are trying to do here? So we just took example 9.5 from the textbook, which is basically defines a specific type of A matrix. Now, what we need to do is we need to find the eigenvalues of the A matrix. And to do the eigenvalue, to find the eigenvalues of A matrix, what you have to basically see is the equation or basically the determinant of the matrix that you need to solve is will be like this. Take the determinant of that, set it equals to 0, and that will give you the specific eigenvalues. So can you guys basically, I mean, without looking at the answer from the textbook, can you please go and solve this determinant and let me know what the eigenvalues would be? We will be doing it together here. So it will be 6 minus lambda times 6 minus lambda, 8 minus lambda minus plus 2, -1, -2 times 8 minus lambda, -2 times 2 equals 0. So if I look at that equation, it will be 6 minus lambda square, 8 minus lambda plus 2 times 6 minus lambda plus 2 times 8 minus lambda minus 4 equals 0. So if I take 6 minus lambda, 8 minus lambda common, I get 6 minus lambda plus 2. Sorry, it cannot be like this. So I need to basically solve this separately. It will be 12 minus 2 lambda plus 16 minus 2 lambda minus 4. So 12 minus 2 lambda, 16 minus 2 lambda minus 4, that's fine. 28 minus 4 lambda minus 4, that will be 24. Then 4, 6 minus lambda. 6 minus lambda square, 8 minus lambda plus 4 times 6 minus lambda equals 0. So 6 minus lambda, then I have 6 minus lambda, 8 minus lambda plus 4. So one of them eigenvalue is 6. Another one would be solved using this quadratic equation. So it will be -48 minus 14 lambda plus lambda square plus 4 equals 0. So lambda square minus 14 lambda plus 52 equals 0. So have you get the values of lambda for this? Or have you been able to find the determinant? I'm just asking you guys to also solve so that just we basically know how we are getting that. I mean, just solving that min matrix in MATLAB is easier, but just I want you to also go through the steps so that we know exactly what we are doing in this case. And can you guys help me in finding out the other two lambdas here?
I got.
Sorry? Oh, okay, so I just copied one term incorrectly, and that was this. This is not -2. This is actually just 2. So if that is just true, so let me see where we are making the changes. So 6, this remains the same. -1, this will be plus. Okay, and that's remains same as it is. So 6 minus lambda square, that remains the same. Instead of plus, you have minus -4. So now you have 12 minus 2 lambda, -16 plus 2 lambda minus 4. So 2 lambda goes away, 12 minus 16.
Professor, I got one of the values is 4. I don't know if that's correct.
I'm just going through this. Just give me a second. I incorrectly put here -2 while copying the matrix. So just let me correct this calculation and I'll come back to you. Okay. Just give me a second.
Right.
6 minus lambda square, 12 minus 2 lambda, -16 plus 2 lambda. This cancels out. And you have my -4 and -4, that becomes -8.
Professor, wouldn't the sign of the 4 also change? The -4 shouldn't it be +4?
Just looking at that, and this is -2. Yeah, you are right. This is -2, and that is +4. You are right. Okay, so that basically terms totally vanishes away. And what you are left with is just this term. So you don't have the quadratic. So sorry for the calculations here. So eventually what you actually will end up, there were some negatives and pluses that I somehow was not taking care of correctly. But eventually when you take care of all the signs, you will basically end up with this equation, right? 6 minus lambda square, 8 minus lambda is equals to 0, and lambdas are basically 6, 6, and 8. These are the eigenvalues that you will get. Is everybody now with me?
Yeah, I follow.
Yes, Professor.
Yep, everybody is with me. Just give me a second. I have the. Okay, so somebody, okay, there were some other calculations as well that you guys are sharing, but I believe because of this term, maybe we are making mistakes, but now I believe you guys are with me. So that basically is the eigenvalues that we are getting are 6, 6, and 8. So here for this, the reason I took this specific example, because it shows two things. One, that you have got repeated eigenvalues. Repeated eigenvalues basically means you have one eigenvalue that is being repeated twice. So this is 6. 6 is basically, first of all, this equation has got, it is a 3 by 3 matrix. It has to have 3 eigenvalues. When you take at this root, it basically has, if you look at this, it basically has a root 6 and 8. but you have to be aware that since this matrix is a 3 by 3 matrix, and this has um, basically it is this factor is basically repeated twice. So this eigenvalue is getting repeated twice as well. So there are two eigenvalues which are the uh, same numbers, 6 and 6, same scalar quantities, and that's why we call that as repeated eigenvalues. And the other eigenvalue is just 8. Is everybody with me here?
Yeah.
Basically, you have lambda 1 is equals to 6, lambda 2 is equals to 6, and lambda 3 equals 8. So these are the eigenvalues, and these are repeated eigenvalues. So whenever we have this type of repeated eigenvalues, we basically have to be a bit cautious, bit careful. The reason being the corresponding eigenvectors may or may not be linearly independent, or may not be easy to find. So we have to be a bit cautious about obtaining the eigenvectors corresponding to these repeated eigenvalues. Remember that eigenvectors there have to be two eigenvectors as well, because you have got two eigenvalues. Even if they have the same number, the eigenvectors, there has to be one eigenvector corresponding to lambda 1, and there has to be one eigenvector corresponding to lambda 2. And of course, since lambda 3 is separate, the eigenvector for lambda 3 can be easily found. And the way that we have found our eigenvectors is we solve this equation is equals to 0. So we solve this equation to find the eigenvectors corresponding to each lambda I. So solve the above equation to obtain eigenvectors each lambda i's. Is everybody with me? Yeah?
So far, yes, Professor.
Yeah, any questions, guys? So what we will do next is,
Professor,
yeah, go ahead.
I have a question on like my algebra that I
Yes.
did for solving for the lambda. I'm not sure exactly where I went wrong, but I ended up getting 6 minus, I don't know if this is correct, but I got 8 minus lambda, uh, 8 minus lambda, and then parentheses 6 minus lambda squared minus 2 plus 4 equals 0.
Okay, so can you confirm, is the matrix that you have written, is this same?
Yeah.
Is that same?
Yeah. I
Okay,
ended up changing the sign of the -2 to a +2.
Okay, so the equation that you will basically get by expanding will be this. Can you confirm you're getting this equation by expanding the when calculating while evaluating the determinant of this matrix? Are you getting this equation? Forget about everything else afterwards. Just this, focus on this.
Yes.
Yes?
Yes.
Okay, then thereafter it should be easy, because then it is just a multiplication. So 6 minus lambda multiplies with this. So you get 6 minus lambda squared minus lambda, then 2 times 6 minus lambda. And here it will be -2 times 8 minus lambda plus 4. So is it the same that you are getting?
Okay, what I did was I took out the 8 minus lambda and I
From where? From where?
from hold on, maybe that's where I did it wrong.
Because you cannot take 8 minus lambda from here, because this 2 is basically not having any 8 minus lambda with it.
Okay.
So you can just check the algebra. You will basically end up with the same. So it should be okay.
Okay, yeah.
Let's say if you get this, then what our next step is, for the rest of you guys, I would ask you to find the corresponding eigenvectors for each one of them. So what we will do is we will try to find eigenvectors for lambda 3 equals to 8 and lambda 1 equals 6 and lambda 2 equals to 6. So first we find for lambda 3 equals to 8. So first we will find the eigenvector corresponding to that. And you guys have to basically help me because there will be some calculations involved. So please help me with that. So let me write that equation. So what we have to do is A minus 8I V8. Let's say I'm talking about the or lambda 3 equals 0. So A matrix is 6 minus 8, 1, negative 2, 2, 6 minus 8, 2, 0, negative 1, and 0. Times V with lambda 3 equals 0. So V lambda 3 has got 3 components because it has to be a 3 by 1 vector. This is 3 cross 3, and this 0 is also 3 cross 1. So that basically you have to be careful about when you are doing some matrix equations or dimensions. You have to be careful about. Okay, so if I have to solve for V lambda 3, then what I will do, I will write an augmented matrix form 0, 2, negative 2, 2, 0. Just let me know if I'm making any mistake. There is a possibility that I may be making some mistake on the plus minus sign or some numbers. So just let me know if I'm making any mistake here. Okay, so that's it. Yeah, is everybody with me so far?
Yeah.
Yes, Professor.
Okay, so if you guys are with me so far, 6, 1, negative 2, plus 2, 6. Negative 2, negative 2, 0, 1, negative 2, 2. I'm just checking again. Okay, so that's the case. So now if you have to solve for V1, V2, and V3, what can be done basically? So we can basically just use simple Gaussian elimination first, or basically if I just add these two rows, what I will get is negative 2, 1, negative 2, 0, negative 1, 0, 0, negative 1, 0, 0, 0. Oh, yeah, 0. That's it. I just add these two rows together, and that's what I'm getting here. So I'm just doing some simple Gaussian elimination operations to solve quickly for the unknown vector V. Now here, if I basically subtract again this with this term, so I just subtract this and this, what I end up with negative 2, 1, negative 2, 0, 0, negative 1, 0, 0, 0, 0, 0, 0. So basically you see that there is infinite solution again, as we know that for eigenvectors. So V lambda 3, one component, V lambda 3, second component, V lambda 3, third component. Basically that vector, eigenvector has got lambda 3, I mean for corresponding to lambda 3 has got 3 components, and it has got the last row, which basically is all zeros. That means it has got infinite solution. And if I basically plug in the equation, it will basically say that if V lambda 3 is 1, it is an assumed value. It can be any number of your choice, but let's say if that is the assumed value, then what will be V lambda 3, 2 will be 0 because that's from the second. I'm just doing back substitution. So V lambda 3, 2 will be 0, and then V lambda 3, the first component from the first equation, using back substitution would be negative 2, negative 1. So the eigenvector V lambda 3 would be negative 1, 0, 1. Is it correct, or is it making sense to everybody so far? Guys, are you with me?
Yeah, I'm just checking it right now.
So far, so good.
Great. So that's for lambda 3. Similarly, we have to do for the same calculation for lambda 1 and lambda 2, which is 6. So can you guys do the same thing? And we are going to do the same thing. And the reason I'm doing this I'm taking this specific example because instead of just taking a generic variable or just describing or discussing everything in terms of generic variables, it will be easy if we see the calculation. So that's why I'm just using this specific equation here. V lambda 2. So let's say we start with V lambda 1. And we see that how from the same equation, whether we will be able to find a different eigenvector. So if we do A minus 6I, I will get 0, 1, negative 2, 2, 0, 2, 0, negative 1, and 2. 0, 0, 0. Now what I will do, I will just add these two rows together. Then what will I get is 0, 1, negative 2, 2, 0, 2, 0, 0, 0. Again, there is one independent variable or basically one infinite solution, and one of them is basically independent of all. So you basically get V lambda 1, the first component, V lambda 1, the second component, V lambda 1, the third component by back substitution. So you can solve that. So first we will assume the third component as 1. You can assume any number of your choice. It may be negative 1, negative 10, 10, 5, whatever choice is. So assuming this is the value for the third component, what we will do is now we can find V lambda 1 second component, which is 2. And V lambda 1, the first component will be 0. So the eigenvector, one of that eigenvector would be 0, 2, 1. Am I making correct calculations, guys, so far?
Yes, Professor.
I'm just checking again. Okay, so assuming that I'm not making any mistakes.
Professor, how did we get to 200 on the row above?
Yeah,
I think I missed a step there.
No,
Yeah.
you are right. This is 202. Thank you for correcting me.
Mhm.
Then this will be negative 1, not 0. So negative 1 to 1. So yeah, okay. Now, am I making correct calculations, guys? I mean, please check and if I'm making any mistakes so that I can correct that.
That answer checks out with the book.
Sorry?
That answer matches up with what I had and also matches up with what the book has as well.
Okay, great. So that's basically what, assuming that these calculations are correct, this basically gives you another eigenvector. So one of the eigenvector is this one, another eigenvector is this one. But remember that with this eigenvalue, we need to have another eigenvector. So we are not getting another eigenvector unless we have 2 rows of zeros, all zeros. Then if you have 2 rows of all zeros, then you have the choice of assuming any value for 2 of these components, and you get 2 independent eigenvectors. But now, because there is only 1 row all zeros, that means you have only one choice of the independent variable. That is, you can make only one choice for one variable. So corresponding whatever choice you make, then basically means everything else, all the other components will be will be based on your choice of this number. So basically, if you let's say if you assume this as 2, can you do the calculation and let me know what are the other components you will get? So assuming that somebody says, okay, why should I assume 1? If I assume 2, I may get another eigenvector. So that's what I'm asking. Is let's say that assumed value is 2. So what will be the other values? Can you quickly calculate it? Do you see what I'm saying, guys? What do you see my point? What I'm basically leading you to?
So you're saying that like for the same corresponding value of the other 6, you can't have the same numbers for the vectors, right?
Yeah, I'm asking you guys that, first of all, I'm just mentioning you that since this is a repeated eigenvalue, then I must have 2 independent or 2 not independent, but 2 eigenvectors corresponding to this, because this it is repeated twice. This root is being repeated twice. Now, when we solve this equation, we end up with this vector. Now, this is one eigenvector. So but you know that there has to be 2. So somebody of you may think that, okay, I took 1, I will take as different assumption for this component and I will get different eigenvector. So I'm just asking you to say that let's say if this is 2, that's an assumption, what will be the other 2 components? And I will then explain you what I basically mean by this specific line of thinking. So somebody tells me.
I got that lambda 1, 2 is 4, and then lambda 1, 1, lambda 1, 1 is -2.
That's what you are getting?
Yes.
Yeah. So you see that if you basically this vector and this vector are not independent of each other. It is basically just depends on. So you multiply this by 2, everything else will be basically multiplied by 2. So you get -2, you multiply this by 2 and you actually get this eigenvector. So whatever assumption you will take about this component, the other components will get proportionally scaled up. So if you take as 5, so everything will be just multiple of 5. So you basically end up with another eigenvector, which is just like the scaled version of this first. So there is not any specific new vector that you are getting, or you are not getting a new direction. That's what I mean to say. So if this eigenvector represents one direction, so let's say it is in 2-dimensional case and represents one direction, which is this lambda 1, this direction. Now the different eigenvector will not give you any other direction. It will again point to the same direction, but with different scaling. So you will actually point to the same direction again. So it's basically the same directions. You're not getting a different directions. But eigenvectors, as we know that it must point to a different direction. That's what I basically mean. Yeah. Are you guys getting what I'm saying here?
Yes, Professor.
Yes.
Yeah, everybody is with me so far? If you're not understanding, please let me know. I'll try to explain again. So assuming everybody is with me, then
Wait,
what?
Professor?
Yeah, go ahead.
I actually have a question, and there's actually another student that has the same question in the chat box. But can the other vector, can it also be the same as -1, 2, and 1?
No, it cannot be, because then it is basically pointing in the same direction.
Okay.
So I need an eigenvector that is not pointing in this direction.
Okay.
Because then basically when you take the other eigenvector the same, it basically means there is no different directions. But as I said, that even if the value is repeated, the vector will not point to the same direction. Vector will be has to point in different direction. It has to be different eigenvector.
Okay. Got it. Thank you.
Yep. Are you guys getting what I'm trying to say here?
Yeah, I follow you.
Yeah. So then how to calculate that specific other eigenvector that is basically missing? We call that as a missing eigenvector. And the way that you actually calculate that is by solving this equation. V lambda 1 missing is equal to V lambda 1 available. So we call this as generalized eigenvector. because this is basically comes from solving this equation where you have one eigenvector missing corresponding to a repeated root, and you are now solving not this equation where a minus lambda I times v equals 0, but instead you are using this equation to solve. So can you guys solve this equation to find what is that lambda 1 missing? So I will have the same augmented matrix, everything will remain same. Not, I mean, we will start with this actually and see how we actually end up calculating v lambda 1 missing. So we have 0, 1, negative 2, 2, 0, 2, 0, negative 1, 2. And here we will, instead of zeros, we will have the available eigenvector, negative 1, 2, 1. Is everybody with me so far? So
Yeah, I'm with you.
I am basically using v lambda 1 available. So that is their augmented matrix. Ax equals b. I'm solving Ax equals b. So a, b basically comes here. So instead of all zeros, I have this available vector basically comes out here. Now you do the same Gaussian elimination operation. Basically, I'm doing the first and third row addition. So I will end up with 0, 1, negative 2, negative 1. And please check whether I'm making mistake or not. That is possible. 2, 0, 0, 0, and 0. So here we basically end up with this row again. That means we can assume the third component as independent of our choice. So v lambda 1 missing, third component is as 1, assume. And can you find the second and first component? So v lambda 1 missing, second component would be half, solving this, and v lambda 1 missing, first component would be 0. Please check whether I am making mistake or not here.
Professor, wouldn't v lambda 1 missing 2 be 1?
Yes, that's what I was also checking. Thank you. So that means the other vector that v lambda 1 missing is 0, 1, 1. And this is different from this eigenvector. I mean, the directions are very different. They are not basically the same, pointing the same direction. Are you getting what I'm trying to say here, guys?
Yes, Professor.
Is everybody with me?
Can you talk about v lambda 1 missing again?
Sorry? Sorry, come again, please.
Start again. V lambda 1 missing.
I'm not getting your question. Can you please speak a bit louder?
Can you one more time explain v lambda 1 missing?
Okay, so what we are doing here, we are trying to find the eigenvectors corresponding to this eigenvalue, right? And this eigenvalue we know has been repeated twice. It is basically coming, it has if you look at the solution, it has got, there are two eigenvalues which have the same number, same value, 6 and 6. So that means for each lambda, there has to be one eigenvector. As we just know from our definition of eigenvalues, for each lambda, there has to be one eigenvalue or eigenvector. So for 6, there has to be an eigenvector. Now, since this 6 is being repeated twice, so there is another direction which basically satisfies the same equation. That's what we mean by different eigenvectors or different directions of the eigenvectors. If the eigenvectors remain the same, basically that means there is no point of having two repeated roots. It's basically just same as only one root. So the reason that it has got two same roots, that means it has got two eigenvectors and they are pointing in different directions. That's what we are interested to find. Now, to find the equation or to solve for the eigenvectors, we basically solve this equation, and using this equation, we saw that we only got one eigenvector, which is this. So to find another eigenvector, what we need to do is we need to solve this equation where instead of saying a minus lambda I times v equals 0, we are saying lambda 1 missing is equals to whatever is available. Available is our this one. This is our available. Okay.
Yes, thank you.
Are you with me, or you are getting what your doubts were?
Yes, thank you.
Okay, thanks. So is everybody with me on the same page?
Yes, Professor.
Yes.
No, I don't get it, but yeah.
Who is having the question? Please let me know. I mean, I tried explaining. Karthik. So which point you are not getting?
I just don't get why we're solving for a missing.
Yes. This one.
Yeah, I don't get that.
So as I just was mentioning a bit ago, that since I have got repeated roots, I must have two directions that satisfies the same equation. It is basically with this specific presence of repeated roots means I have two different vectors, not just one vector, which corresponds to lambda is equals to 6. That's what I basically mean by finding a different eigenvector.
But I thought, okay, so my concern is I thought we had already solved for that other repeated one. Wouldn't it be negative like 2, 4, 2?
It cannot be. So as I was mentioning, that if I have negative 2, 4, 2, it is the same direction as this. So there is basically this eigenvector and let's say I have lambda 1 missing. Is there, so when I say, first of all, we know that eigenvectors are basically representing directions. Eigenvectors represent directions, not magnitude. We actually saw that in the last lecture, right? Are you guys with me? Eigenvectors represent direction. It does not represent the magnitude. So
okay.
The reason I'm saying it's direction because this number is based on your choice. So suppose somebody says I am going to take it as 0. So you can take it as 0, but then there are, based on that, you will get a specific, I won't say you can take it as 0 because it has to be other than 0. Other than 0, any number of your choice, negative 1, 1, 10, 5, whatever the number of your choice. So based on that number, you will get these specific other components, 2 components, right? I took it as 1 and I got 2 and negative 1. Somebody says that that he wants to take number 2, or basically assume that is 2, then he will get 4 and negative 2. But when you look at these are basically the same directions. It is basically pointing in the same direction. So these vectors are not different because eigenvectors basically represent the directions.
Okay.
So to get a different eigenvector corresponding to this repeated root, which represents another direction, I am solving this equation.
Okay.
And that basically gives me this lambda 1 missing. So this is not lambda 1 missing. This is not independent of my, so not independent of v lambda 1 already calculated available. So that's why it cannot be the second eigenvector. Because then if it is a second eigenvector, somebody say, okay, I will take 3. V lambda 3 as 3, then you will get 3, 6, negative 3. So that will be a third eigenvector. Somebody say, okay, he wants to take 4, then it will be 4, 8, negative, negative 4, 8, 4. It will be, but that is basically pointless to argument because you are just scaling up the directions. And when you scale up the direction does not change. It will basically be in the same direction. Is everybody with me so far?
So I guess the rule is for every eigenvalue, it has to have a specific eigenvector. Is that what it is? Like no one.
Yes. For every eigenvalue, there has to be one eigenvector, and that eigenvector represents a direction. It has to be a different direction than your original one, whatever direction you are getting. So if you are getting two eigenvalues, two repeated eigenvalues, which have the same same scalar magnitude, the directions will be different. You will get one direction as this, another one will be this. Let me know, you guys with me are with me or not.
Yeah, I follow. Makes sense.
Yes, I follow.
Okay, so the next thing, the last thing that we are doing here is what is eigen? Sorry.
I have one quick question.
Go ahead.
So why did you? I just don't get that equation. Like, why did you set it equal to the available one?
So this is the, okay, so if you ask me how do I get this equation, then I do not have the answer for you at this point of time. So this is how the missing vectors are calculated. So if you ask me the proof of this equation, I need to basically get back to you. I have to basically look and read about it, that why this, how this equation has come. I'm just telling you that this is the way that you can calculate the missing vector.
Okay, got it. All right.
At this point, I am not able to give you the proof of why we get this equation, how we get this equation.
Okay, got it.
Okay, good. So, okay. So the last thing that we are basically doing here is that we are going to create a matrix of the eigenvectors we have got. So we have got V lambda 1 available, V lambda 1 missing, and V lambda 3. So that will be the eigenvector. So that you basically get a matrix, and we call that as matrix as Q. So if I basically create a matrix Q by basically creating the vectors and arranging them in this column format, then what I will get, my one of the eigenvector that I got is -1, 2, 1. Missing was 0, 1, 1. And lambda 3 we got as -1, 0, 1. Is everybody with me?
Yes.
This is your V lambda 1 available. That's what we calculated. This is your V lambda 1 missing. That's what we calculated a bit earlier. And this column is basically V lambda 3. Yeah, is everybody with me?
Yes.
Now what you have to do is you basically multiply. If you have the MATLAB, I mean, I'm not expecting you to do by this calculation by hand. Just multiply this and see what is the result you are getting. If you have a MATLAB, you can basically put Q matrix as this, A matrix you already know, and you basically do this matrix multiplication. Yes, you got. So one of them, yeah, okay. So I'm getting, as you guys have just did that, and that's basically the correct one. So it is basically you're getting 6, 1, 0, 0, 6, 0, 0, 0, 8. So this is basically called as, I mean, this matrix we call as Jordan canonical form. So this is basically called as a Jordan matrix. Jordan canonical form. Canonical form basically means that if my eigenvectors would have been all independent, this lambda 1 missing, I mean, if I would have, let's say, if I would have lambda 1, lambda 2, and lambda 3 all distinct, if lambda 1, lambda 2, lambda 3 are all distinct eigenvalues, real eigenvalues, they will result in V1, V2, and V3 independent eigenvectors. Independent eigenvectors. And if that would have been the case, then if I would have make a matrix out of these independent eigenvectors, V1, V2, V3, and I would have this matrix multiplication that I have just asked you now, I would have got lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. That's what the matrix I will got. And that is the matrix we will be using for diagonalization. This is the matrix is in it's a diagonal matrix, and the diagonal of elements are basically your eigenvalues with eigenvalues along the diagonal. However,
Professor, does that say Jordan something?
canonical, K-C-A-N-O-N-I-C-A-L, canonical form, or Jordan matrix. We call this or just say it's the Jordan matrix. That's it. That should be fine as well. So what I was saying that if your lambda 1, lambda 2, lambda 3, it can be lambda 4, lambda 5, all can be higher lambdas as well. But if you have this different distinct real eigenvalues, they will correspond to independent eigenvectors. And each of the eigenvectors, if you are basically assembling them in a matrix, we call it as P, and you are doing this matrix multiplication, you will see that this A matrix converts into a diagonal matrix. So all the elements of that diagonal matrix will be your eigenvalues. And this is what we call as diagonalization. So you basically can diagonalize, or basically if you have any matrix A matrix, if you remember, it is not a diagonal form. Remember that A is basically a standard matrix. And if you do this matrix multiplication with P inverse AP, you basically end up with a matrix which are all diagonals, and diagonal elements are your eigenvalues. But if you do not have these distinct eigenvalues, then you will have the case where some of them will be missing, just like this. So in that case, when you do the same operation where you assemble all the eigenvectors in this column format, and then you do this matrix multiplication, then you will basically end up with this Jordan matrix where your diagonal elements will still be your eigenvalues, but you will have one of the element will be non-zero, which will be in the upper diagonal form, and that will be have number 1 in it. So it basically is the Jordan block form. This is your eigenvalue, 8 is your eigenvalue, 6 and 6 are your eigenvalues that you have calculated, but instead of 0 here, you will have 1 at the upper right corner. This is what we call as Jordan matrix. And when you multiply this, it is not just like a diagonal form, but it is basically very close to the diagonal form, but it is not exactly diagonal form. So that is what we call as Jordan matrix. Are you guys getting what I'm trying to say?
So if we do the same for the first example, we're going to get exactly that defined Jordan matrix then, because everything's independent.
Come again, sorry, what is that question?
So if we do that the same to the first question that we answered, everything will be defined. So that we will see the diagonal matrix format. 100%.
Yeah, if you have independent or distinct eigenvalues, they are not repeated, any one of them are not repeated, then you will got independent eigenvectors and you will get this in diagonal form, all lambdas. Are you guys following what I'm trying to say here?
Yeah, Professor,
Yes.
is there a purpose we use this matrix for something, or?
Yeah, we are going to use this. So who is this? Sorry, I've missed that.
It's me, Mohammed.
Okay, so yes, so today we do not have the sufficient time to actually extend our discussion beyond this, but we will see in the next lecture why we actually use these matrices and what is the specific purpose. So let me actually wrap up our discussion with the.
I have a question.
Okay, go ahead.
Can all the eigenvalues be the same? All the lambdas have the same value?
Yes, of course, it can be same. Then in that case, you will have two missing, or basically you will have, like, depending on your eigenvalues, you will have different missing vectors, and you have to calculate that. Just using the equation that we have been solving, this is what we were basically using the equation to find the missing eigenvector. So you can have three eigenvalues that have the same repeated roots. So you can have 6 repeating 3 times. That means possible. Yes.
Okay, got it. Thank you.
Yeah. So please remember though that even if you have 3 eigenvalues, the eigenvectors corresponding to those should be in a different direction. That's what this matrix is made up of. It's made up of 3 eigenvectors and they are different directions. If they are the same direction, then this matrix will become singular. And we don't want this matrix to be singular. We want this to be non-singular. And the reason we want to be non-singular, because we are taking the inverse of that while doing this multiplication. So when we're taking the inverse, if it is a singular matrix, then we cannot take the inverse. That means the determinant will be 0. So that is why we need all the different columns has to be independent of each other. And that is the reason we cannot, that is the reason we basically need 3 different directions or 3 different independent vectors to construct our matrix. So I was basically wrapping up our discussion that we are going to use this form of matrices or diagonalization to solve differential equations, ordinary differential equations. So you will have second order differential equation or nth order, higher order differential equations or first order differential equations. So let's say you have a specific differential equation like, this is what basically taking from the discussion from the textbook itself. So you have a second order differential equation where x double dot basically means it is a acceleration vector, it is time derivative twice and taking derivative with respect to time. And A is the matrix form, X again is a state, is a variable, and these are all vectors. So X basically is X1 of t, X2 of t, it can be displacement, velocity, acceleration, or any other physical parameter of interest. So it is basically a vector. So this is not just one equation, but it's a system of second order differential equations, and where X is your unknown vector. And A matrix, because it is not a diagonal form, it is basically coupled. So you cannot solve this equation just using the standard solution you have learned so far in your 501. If you have done that, solving ordinary differential equations, you cannot use that solution because now your A matrix is not is basically generic form, it is coupled. So we will use this type of calculations or this type of multiplications to make our differential equation just like a diagonal form. That means each of the equations will be separated out, it will be uncoupled. So we'll discuss more. Actually, it will not make more sense today at this point of time to go or discuss beyond this, but we will definitely use these formulations in our discussions next while solving the differential equations. Make sense, guys?
Yes, Professor.
Are you guys with me? So forget about what I was saying in the last part because it doesn't make sense to extend our discussion beyond this. The only thing I was basically saying that we will be using these matrix multiplication and see how we can use them in applications and what is the use of that in our next lecture. But if you have got on whatever we have done so far, let me know if you have any doubts or any concerns or anything, any questions.
All right, thank you.
Yeah, welcome. Okay, if there are no other questions, we are going to wrap it up today, but I will take your individual questions about any problems, homework that you are facing and try to address them. So let me know if you guys have any other problems.